Okay, thank you very much. This is a terrible video. Well, my name is José María Torres, and the first thing I want to do is to speak about the objective of this presentation. This is a business-oriented presentation, and we are trying to help the business units in a decision-making process that probably almost every company have to do, and is the portfolio optimization. And also we are going to see the overview, the methodological approach to this problem, and we are going to see how we try to solve this problem. First of all, key figures about the company. Telefonica is a telecom company with a strong presence in Europe, Germany, UK, and Spain, and also in Latin America. We have operational business in 14 countries, and we have presence in 24. We are more than 120,000 professionals with revenues over 48 million euros, and more than 346 millions of total accesses. Total accesses, that means mobile lines, prepaid, postpaid, machine-to-machine, landlines, TV connections, and also internet connections. Our brands are Telefonica. Telefonica is the institutional brand, but we are using 3 commercial brands. We are using O2 in UK and Germany, probably you know that. We are using also Vivo in Brazil, and we are using Movistar in the rest of the countries that are Spain and all Latin America, but Brazil. And here I am. Inside Telefonica, we are in the Chief Data Office unit, and inside the Chief Data Office unit, there is a key unit that we call the FOR platform. As I told before, we are in 14 different countries with 14 different histories. In Germany and UK, we are mobile. In Spain, for example, we are an incumbent company. And in Mexico, for example, we are a very small company with mobile customers. So in each company, we have different data, we have different histories, and we have different ways to organize this information. So this FOR platform tries to normalize the information across all the footprint, across the 14 countries, trying to do easy the development of new products and services for the customers, but also for the internal customers, for example, the marketing units. Inside this FOR platform, there are a unit that we call the internal use cases and market research. The internal use cases tries to develop new products and services for marketing units, mainly recommenders, and the market research units, what it's doing now is hear the customers, trying to understand what customers want, what customers like, and also what customers need. So in the internal use cases and market research unit, we have experts in customer insights, in market research, in customer behavior, also in artificial intelligence, in big data, and also in product design. We like to present ourselves with this picture. This picture is the School of Athens and represents the main ancient Greek philosophers discussing about how they see the world and maybe also about how the world should be. And this unit, the internal use cases and market research, we think that is represented in this picture in the center of the picture, represented by these 2 philosophers, Plato and Aristotle. If you see, Plato, with the hand pointing to the sky, is representing the ideas world. Is representing what customers want, what customers like, what customers need, and then market research is represented by this philosopher. In the other side, Aristotle, with the hand parallel to the floor, represents the facts, the observation, and the experience. So Aristotle, in this picture, is representing the big data unit or the internal use case unit. And both of them are discussing, as we discuss in our units, about how to use the best part of the market research and place together with the best part of the big data to obtain better products for our customers, but also better products for our internal customers. And now the question and the problem that we want to solve. One day, the business unit or the marketing unit or the product unit come to see you and say that they are developing a new portfolio, and probably we can help them with the optimization on that portfolio. In the telecom market, the portfolios are very complicated. Probably every company can say the same. But in our case, this is very complicated because we have a lot of different products. As a telecom company, we are offering fixed telephone products. We are offering internet and mobile data products, also pay TV, also mobile prepaid, contract, and we are adding more value-added services like football, movies, series, sports, music, etc., and etc. This is a very complex market for us also because, as I told before, we are presented in 14 different markets. And in these markets, our history is completely different. And we have different competitors, we have different facilities, we have different infrastructure. In some countries, we are only mobile. In some countries, we are mobile and fixed. In some countries, we are the incumbents, and in some countries, we are attackers. And in each country, we have different brand positions. So we have sometimes in advantage and sometimes in disadvantage with the different competitors. And also, it's complicated, or is a complex market, because we have a lot of customers in a lot of different countries. As I told before also, we have 340 million different accesses, and every customer has different needs, likes different things, wants different things, and different customers are in different socioeconomic segments, so the needs of the different customers are different. The first main question also creates more and more smaller questions that we have to answer together with the main one. For example, how many tiers should have in my portfolio? Which internet speed for each tier? Which price for each tier? How many gigabytes? I have to include TV, I have to include series, movies, I have to include football, I have to include other sports, I have to include music, other value-added services, and in which tiers, and with which prices for each tier. And also, if I want to obtain a good portfolio, I don't have to forget that we are not in a monopolistic market, and there are competitors. So when we are going to define the new portfolio, we have to think about which should we do if my competitors reduce the price or increase the value-added services in the different tiers, if include a new tier, if reduce the tiers, if do any change that the competitors can do, because, of course, they are autonomous. To solve this problem, or to give an answer to this problem, we are dividing the big problem in some steps. We are trying to answer what do customers want, what can we offer to the customers, how can the competitors react, and also what does optimization means. Let's go step by step, and then we are trying to answer the first one. What do customers want? In order to answer these questions, what we are doing are building a virtual market. A virtual market takes into account first the products that the customers already have. Then we are including also the declared desired product. That is, the first point is the big data. The second point is market research. And then with data science, we are trying to modelize the behavior using these both parts, what customers have and what customers want. And then we build a virtual market. A virtual market is a group of virtual customers. So it's easy, but the question then is, what is a virtual customer? A virtual customer is a simulated customers obtained from market research and big data. And the important thing is that each virtual customer can tell us which is the preferred option when we are showing them the total portfolio in the market. Not only our portfolio, but also the portfolio of the competitors. So when a virtual customer sees the offer, the offer of the competitors, can say, I prefer this one of your offers, that one of the competitors, or maybe I don't like any of them and I choose the non-option. And Virtual customers are linked to real customers using generic variables like the price, the data, the value-added services that they have, or the customer segmentation, etc., and etc. So at the end, the virtual market is a way to simulate what real customers need and what real customers want. Okay? We are building a simulator. To build this simulator, the first thing we have to do is reduce every product that we can offer to the customers into attributes. There are some examples, of course, this is not an exhaustive example because we can offer a lot of different things in a telecom market to the customers. In this case, we can think about, we can offer TV, different amount of channels, TV, sports, football, etc., series. We can offer the landline, we have offered mobile data for the first line, second line, third line, fourth line, because there are family plans in some countries. We can also divide the product in the internet with the internet speed, and also, very important, the brand. This is a key attribute. And every attribute is divided into levels. For example, the brand, I can be interested in study brand number 1, brand number 2, and brand number 3. And for example, for mobile data, I can be interested in study mobile data between 10 gigabytes up to 50 gigabytes. It's important that even if in our market there are only tariffs up to 20 gigabytes, we should include more gigabytes because maybe we are launching tiers with higher gigabytes in the near future, or we think that the competitors are launching more gigabytes in the future. So if we want that our simulator is valid for the following months, it's important to take into account not only the real offers at the moment, but also the future offers that we think that they are going to be available in the market. Then we place price for every attribute and every level. For example, for the brand, we are not placing price, but for mobile data, we are giving a price of $10, $20, and $30 for the 10, 20, and 50 gigabytes. And as we are interested in the price sensibility, because price sensibility is one of the first simulations that we have to do, we are showing different prices for the same attributes to different customers. So maybe customer number 1 is seeing $10, $20, and $30 for 10, 20, and 50 gigabytes, by customer number 2 are seeing the prices at 7, 14, and 24. So every customer is building the ideal product, and maybe customer number 1 choose only 10 gigabytes because he doesn't want to spend more than $10, but maybe customer number 2 is choosing 20 gigabytes because for him the $14 is cheap enough. At the end, what we are obtaining is the probability for every possible product. That is, we can, at the end, see the research and see how many times each different product has been chosen. And we are translating these probabilities into mathematical quantities that are called utilities. To obtain these utilities, we are placing some set of equations with the explained variables that we have to obtain is the utility for every attribute and every level for every customer, and we have the overall probabilities of every product obtained from the research. So that we are obtaining is the utility for every level and for every attribute and every level. And we are obtaining things like that. We are obtaining graphs that says, for example, for the brand there. Say for this customer, the utility of brand number 2 is the highest one, and then the utility for brand number 2 is the second highest one. And these utilities are higher than the utility for the different brands. What we are obtaining here is for this individual customer, which are the preferred brands, And this difference of utility can be translated into euros or dollars. So what we are seeing here is the extra amount of money that the customer can pay for brand number 2 over brand number 2, for brand number 1, for over brand number 2, 3, 4, etc., etc. That is, we are obtaining the premium price of the different brands. And for the data, we are obtaining the utility from, for example, 5 gigabytes up to 50 gigabytes. And for this customer, that we are obtaining is moving from 5 gigabytes to 10 gigabytes has an extra utility very high. However, the extra utility is reducing if we are adding more and more gigabytes. So if we translate this utility into money, that we can do that, we can obtain how much the different customers can pay for the extra data from 5 to 10, from 10 to 20, from 20 to 30, to 30 and 40. So we can obtain the price for every customer, for every level, and for every attribute. So when we show a customer different options to choose, for example, in this case, we have brand number 1, 10 gigabytes of data, 10 megabytes per second in the internet, and 50 channels of TV for this price. Then the option B, brand number 2, more expensive but with more things, and brand number 3, and option C with brand number 3, more data, more speed, more channels, and more price. The customers can think, okay, I don't want to spend a lot of money, so I choose option A because it's the cheapest, and we have enough data, enough channels, and it's enough. Or maybe the customer can say, I need a lot of data and a lot of channels, so I can pay and I can afford this amount of money, so I will choose option C. Or maybe the customer can say, I don't want A, I don't like B, I don't like C, I can choose the none option, so you should offer me a different option if you want to buy something in the market. The second part is what can we offer and how can react the competitors. What can we offer is very easy because we can offer whatever we want. We can offer whatever we want in gigabytes, in minutes, in mobile and fixed, the internet speed and price, always keeping the company profitable. We can also add more content like series, movies, sports, football, whatever we want. And we can also value-added services like video, music, social networks, etc. And the same for the competitors. The competitors can offer any amount of data, minutes, internet speed, price, always keeping the company profitable. They can also include more content like series, movies, sports, and also more video services like music, video. This is important in this point that maybe you include the market intelligence unit because they have information about what the competitors can do. To what extent they can reduce price, to what extent they can increase speed, they can increase the amount of data, etc., etc. And finally, the last question is, what does optimization mean? And this is a good question, and this is the most complicated part, because we are not in a monopolistic market. So we cannot speak here about optimization because optimization is when we are taking decisions under certainty. And in this case, we are not alone in the market. There are more and more competitors, 4, 5, 6, even 10 or more competitors. So we are making decisions under risk. So what we have to introduce in the company, the first thing that we have to do is to introduce a game vision theory in order to tell the company that our decisions, if we are trying to optimize the portfolio, can impact in the results of the competitors. If we are increasing our profits, probably is because the profits of the competitors are reducing. And if the revenues or profits of the competitors are reducing, then the competitors can start retaliating actions, and then a price war can start. In order to introduce this game vision in the company, the first thing we have to do is to define the different strategies that we have and the competitors have. And these strategies are infinite. If we are starting from the current portfolio, we can increase the price by 1 cent, 2 cents, 3 cents, €1, €1 and a cent, €2, €3, whatever we want. Or we can include more tiers, we can reduce tiers, we can include, increase the speed of internet, reduce the speed. So we have, and the competitors have, infinite strategies. We need also the payoff matrix. The payoff matrix is which are my profits and the profits of the competitors for every combination of my strategies and the strategies of the competitors. And to do that, we are developing before the virtual market, because the virtual market, as in the virtual market, every customer says what is the preferred option, we can obtain the profits for every combination of our strategies and the strategies of the competitors. And at the end, we have to also define how we are reaching the equilibrium solution. And to do that, we are using Monte Carlo and game theory, because, as I said before, we are not speaking about optimization, we have to speak about equilibrium solutions. To speak about this game theory part, first, I want to introduce very fast the classical prisoner dilemma. The classical prisoner dilemma allows us to introduce two key concepts. The prisoner dilemma, probably you know, there are two prisoners with two strategies each one, to stay silent and to confess. Here we have the two strategies for A, here we have the two strategies for B. And the four elements of the matrix are the payoff for player A, and the second is the payoff for player B. In this case, we can speak about years in jail. For example, see, if player A stays silent, player B stays silent, both of them go 1 year to jail. If player A confesses, player B stays silent, player A goes 0 years to jail, and player B goes 8 years to jail. The first key concept that we can introduce with this game is the Nash equilibrium point. The Nash equilibrium point is the point from which none of the players has an incentive to go out of that point. For example, in this case is confess, confess. In this combination, both of them go 4 years to jail. 4 years A, 4 years B. If the player A tries to move from confess to stay silent, then player A will go 8 years instead of only 4. That player A has no incentive to leave the equilibrium point. And the same for player B, because if player B changes the strategy, then player B will go 8 years to jail instead of only 4. This is an equilibrium point. And the second key concept is the Pareto optimal point. The Pareto optimal point is the point where both of the players obtain in overall the best results. And in this case is to stay silent and silent, because in this case they will go 2 years to jail in total, and in any other combination will go 8, and also 8 years to jail. The problem of the Pareto optimal point is that this is not an equilibrium point. And maybe if we are starting here, maybe player A tries to change to confess, because he thinks, if I confess instead of stay silent, I will go only 0 years instead of 1. And the same for player B. But once player A has moved to this point, then player B will move to that point, and there is no back to the equilibrium, to the optimum the Pareto optimum point. This Pareto optimal point and the game theory can be extrapolated to the company competition, because can be extrapolated to the company competition because can be explained the price war that a company can start at any moment. And other game very well known by everybody is the rock, scissors, paper game, with 2 players have 3 different strategies: rock, paper, and scissors, rock, paper, and scissors. This is a zero-sum game with no win-win solution. So, if one player wins, the other loses. If one player loses, the other wins, or maybe there is a tie. With rock, there is a tie. Player A rock, player B paper, player A lose. And this game is very interesting because it's introducing oscillating solutions. There is no Nash equilibrium point with pure strategies in the game. That if we play this game, we are obtaining oscillating solution. Player A choose rock, then the other paper. Player B paper, then you a scissors. Player A a scissors, the other rock, and so on, and so on, and so on. And let's see the results. For the results, we are using a telecom market, a real telecom market, and we are using realistic scenarios. Not real, not totally real, but realistic scenarios. We are taking into account 3 players, and we are placing 5 equivalent tiers for each one of the players. And we have run 2 simulations. The first simulation is only player A optimize the portfolio. We can speak here about optimization. And the second simulation, all the 3 players try to optimize the portfolio. That is, all the 3 players try to find the equilibrium solution. To do this, we are starting from the initial portfolio, and then we choose a random tier for the player A. This is the first simulation. Only player A is trying to optimize the portfolio. Player A, we choose a random tier selection. We introduce a random change in that tier, and we check if the company A improved the profits. If yes, we accept the change. If a company don't improve the profits, then we reject the change. And then this cycle, we repeat this cycle once and again. So we can introduce a convergence criterion, and if the convergence criterion is reached, then we can leave, and then what we are obtaining here is the ideal portfolio for player A. That is, player A has optimized the portfolio. Here we are presenting the evolution of the profits for the 3 players. As we can expect, only player A increased the profits because both of them, B and C, are not changing the portfolio, cannot defend themselves. So what we are obtaining here is player A is increasing the profits by 25%, player B and C more or less are reducing the profits by 17%. We are seeing here that the convergence is reached very, very fast. In 300, 400 cycles, the criterion more or less is reached. The convergence criterion is reached. The solution, then the interesting thing is to understand what is happening with the portfolio of player A. Here we are seeing the market share of the 5 different tiers of player A. That we are, the tier number 5 is the high value, tier number 1 is the lowest value. That we are seeing is the first tier is more or less constant over the different iterations, and tier number 2 and tier number 3 are reducing the market share. Tier number 4 more or less is constant the market share, and the focus of the strategy of player A should be to increase the market share of tier 5 with price reduction in this tier. But that can start a price war. If the profits, if I am increasing a lot my profits, then what is going to happen is that profits come from the profits of the competitors, B and C. So they can react. They can start retaliating actions, and then we can try what will happen if we allow the 3 players, A, B, and C, to change the portfolios. We start from the initial portfolios of the 3 players. Then we have to choose one random player, A, B, or C. Then we choose a random tier for that player. We introduce a random change for that player, and then we check if that player is increasing or not the profits. If the profits are increased, then we accept the change and we start again. If the profits are not increased, then we reject the change and we start again and again and again. We can try to introduce here a convergence criterion. If a convergence criterion is reached, we can leave the simulations and we can say that an equilibrium has been reached. And we can also introduce a check here in order to avoid price wars. Because maybe the player is increasing the profits, but this increase in the profits are very aggressive. So maybe we can place a margin and say if the increase in my profits, or better, if the reduction in the profits of the competitors is more than 1, 2, 3%, we can reject the change in order to avoid the price risk, the price war risk. Let's see the results. First, like before, what we are doing here is presenting the profit variations for the three players, player A, player B, and player C. What we are seeing here is that no convergence is reached in this game. First, we are starting from here. During the first 1,500 iterations, the profits of the three companies are reducing, and then we are starting in a cyclic solution. So there is an equilibrium, but there is an equilibrium with the oscillations. We are seeing here a maximum of A profits, the maximum of A, the maximum of A, the maximum of B, a maximum of B, a maximum of B, a maximum of C, 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 C. So we can say that this is like we can expect, okay, the reduction in the profits of the three players. With this methodology, what we are doing is that we can quantify the price war risk if we are going to a direct optimization on all of our portfolio. As we can say that our profits can be reduced between 15 and 30%. And here is also interesting, these cyclic solutions, because the first part can be explained using the prisoner dilemma game or something like that, and the second part can be explained using the rock, paper, scissors game or something like that. Of course, every problem can have to be studied one by one. And what is happening with the market shares of all the tiers for player A? We are presenting here again the market share only for player A of the 5 tiers, and we see that for tier number 1, the lowest value is more or less constant over the time. Tier number 2 sometimes drops to 0, so maybe in order to the portfolio optimization or the portfolio simplification, the simulations are saying that tier number 2 can be removed from the offer in a competitive market. Tier number 3 have several oscillations, and the key point is tiers number 4 and number 5, where probably the fight is going harder between player A and the other competitors. Sometimes tier number 5 is the maximum, is the highest has the highest market share. Sometimes it's tier number 4 which have the highest market shares. Okay. What we have so there in the result is that we can quantify the price war danger, okay, in this case, and we can simulate different scenarios, different markets, different competitors. In order to the portfolio simplification, we can think that maybe tier 2 can disappear because sometimes the market share of tier 2 is 0. The focus of the company has to be in the tiers number 4 and tiers number 5, 4 and 5. And we are obtaining here oscillating solutions. So in order to understand the problem, we have to take into account the prisoner dilemma for price war and also the rock, scissors, paper game in order to understand the oscillations. And finally, the conclusions. Probably you have seen the movie Infinity War. In that movie, Doctor Strange looked forward into the future, so 14 million future or 14 million scenarios, and only one, the Avengers win. The tool that we have developed and is like something like the gen of time in order to see all the possible scenarios, and there are 40 millions, even more. And the mission of the internal use cases and market research unit is to look for that one scenarios where we win and make it happen. Okay? Thank you very much.